So in today's lecture, we will discuss what's called high harmonic generation. So the contents for today's lecture will be what is strong field ionization, what is high harmonic generation, and a number of features of this high harmonic generation such as cutoff and chirp can be actually explained using a classical three-step model. So we'll learn about these aspects, and the reference book for this is Fundamentals of Attosecond Optics by Zhenggu Chang. So what is high harmonic generation? So we'll start off with the paper that the Nobel Committee has cited when they gave this Nobel Prize to Professor Annie Heulier. So in this experiment in 1988, this seminal experiment, what they did is they drove xenon gas using a laser with intensity 3 times 10 to the 13 watt per centimeter square. And they found that they could measure harmonics, and these harmonics extended all the way from the third harmonic to all the way up to 21st harmonic. And the important feature is all these harmonic intensities are within the same range, that's they fall into the same order of magnitude. Whereas in the last class, when we looked at the simulations where we computed the harmonic generation, we found that the third versus the fifth, or the first versus the third, had a huge gap. That means there were a factor of 100 or 1000. Whereas in this particular case, they found that all these harmonics had a very similar intensity, maybe over a factor of 10 spread over, and this was an extremely new result. So to understand this high harmonic generation process, so let's fall back onto this model one-dimensional hydrogen atom that I introduced in the last lecture. So just a recap. So this model hydrogen atom is described by this Hamiltonian. This is a H naught. The first term is a kinetic energy and the second term is a potential energy that gives you the same ionization potential as a real hydrogen atom. This is the interaction with the laser field, which looks like P dot E, right? A dipole in the presence of an electric field. That's how the potential looks like. And if you look at all possible eigenstates of the H naught operator, that is without the presence of the field, this is the eigenvalue spectrum. So what you see is there are some negative energy values that's below 0, and there are some positive energy states. Any typical atomic potential would have negative energy states and positive energy states. The negative energy states are the so-called bound states, and the positive energy states are called the continuum states. Okay. Now, x-axis is the just an index. So let's say I compute all the eigen values for this particular Hamiltonian. I need to index them. So this is the first value, the second value. No, it's nothing to do with that here. It's just a one-dimensional problem. So I'm just plotting as a function of some serial number all the eigenvalues in a certain ascending order. Okay. The important note is there are negative energy states and there are positive energy states. They would be called the bound and the continuum states. Now, how do they look? If we look at the spatial profile of these states, so I'm plotting the first few here and the last few here. So that's the blue one is a ground state. So let's say that's a state 1, the green is a first excited state, and this orange is a second excited state. So these are the bound states having the negative energy eigenvalues, and these are localized states. So if you see, you can say there is a particular global maximum to this. There is one more global maximum for the second state, and for the third state you can say that there are 2 maxima. Okay. Whereas if you look at these continuum states, which are the positive energy states, I have plotted a few of them. The exact ordering is not really important, but the main observation that you would make is they are not localized. So they are spread all over, and there is no, of course you can define one particular global maximum, but you see that this is an oscillating wave function. So the electron can be found essentially anywhere. Okay. There is no one particular fixed value which corresponds to the maximum position where you can find the electron. So these are the important characteristics of bound states, which are localized states, and continuum states, which are not localized. These are the negative energy states and these are the positive energy states. Now, if you subject this electron to an external field, how does the ground state modify? Right? This is a plot that demonstrates what happens to this ground state. So that means, let me draw a schematic. So this is the potential V as a function of x, and the ground state looks like that, right? A very well localized around the origin. Now, if you now subject this state to a particular field, the potential overall gets modified to such a form. It gets, you have a linear function that's q times x times f, q f x or ex. This gets added onto this Coulomb potential, it gets distorted, and what is being plotted here is how does this wave function psi square gets modified as the field strength increases. So what you have here is a field strength. This is electric field is equal to 0, electric field is equal to 0.02, 0.03 and so on. Let's first check how does the blue curve look. This is a blue curve. The blue curve is well localized. That's what you have seen in the earlier slide. Now as the field increases, you see that it gets distorted for these couple of small fields, let's say 0.02 and 0.03, it still retains its nature. So if I examine these three states, the blue, orange and the green, they look quite similar, but they get slightly deformed, right? They are still like bound states. Whereas if you keep increasing the field strength, so let's look at the maximum value 0.08, so this is a brown curve, you see that it gets highly oscillatory, right? So you have some bound nature that's given, as well as it gets highly oscillatory, which means if you think about what is the contribution of this state from the bound states as well as the continuum states, you see that if I am able to actually compute what is the projection of my state onto the bound states, right, and compare it with what is the contribution of the state from the continuum states, if I were to decompose this state into the bound and the continuum states, you see that for the low field strengths, it's mostly bound nature because they're well localized. Whereas for the higher field strengths, you see that they become oscillatory, which means they pick up significant continuum character. Okay. So the oscillatory states would correspond to the continuum states. So any question? Maybe I can pause for a moment. So the key takeaway of this part is the following. Let me see a few students here. So I can quickly go back. So we have this Hamiltonian, the model Hamiltonian that we discussed in the last lecture. I plot here the eigenspectrum. So I compute all possible eigenstates for this Hamiltonian. And then we recognize there are so-called negative energy states which are called the bound states, and there are the positive energy states which are the continuum states. If we look at what is the nature of these states, you see that the positive energies, the negative energy states, these are the bound states, they have a localized character if you look at the wave function. Whereas if you look at the positive energy states, they are highly delocalized, okay, and they become oscillatory. Now in the next slide, I showed that what happens if you put an atom in a static field and then look at what happens to the ground state. You see for the weak fields, the state still remains like a bound state, that is they get slightly deformed, right. If you look at the blue, orange and the green curves, they get slightly deformed from the original field is equal to 0 state, but they retain the bound character, which means it has a single maximum. Whereas if you keep increasing the field strength, they become oscillatory, they pick up this oscillatory behavior with multiple local maximum as well. And now if you compare with how do continuum states look like, they have a significant contribution from the continuum states. Okay.
So why is this sort of this continuum contribution only and not symmetric?
Right, because we have picked a particular static field. So this is, I have computed the eigenstate with a particular static field. So therefore I need to choose some direction. So if I had chosen the other direction for the field, then it would be on the other side.
But is there cases where you can
It would depend on the potential. If I have a very simple, so this schematic would help you. So if I have a simple soft core or Coulomb potential and then I have a field such that it deforms in this following way, then the electron can actually tunnel through this, and therefore I have this oscillator behavior on this side. Okay? But the tunnel barrier is high on this side, cannot tunnel through. So therefore you will have such oscillator behavior only on one side.
So this is like it's actually a barrier on the left hand side. That's where you're able to see this continuum contribution there. That's what.
Yes.
So if there's a finite barrier for it, now this is we look like the direction, like the barriers are sort of infinite on both sides. That's why it's just keeping on oscillating, right?
Right. It would just go to infinity. Yeah, it's just there until infinity. In a numerical calculation, you can't go to infinity. So this is just to demonstrate that what is the importance of the continuum states. Okay. Now this also,
So basically, the non-oscillating nature for low fields is because the potential is not still
deformed.
high, so
Yes.
that you can't tunnel.
Right. So what you see is this regime of these weak fields is your conventional nonlinear optics. Okay. So this is conventional nonlinear optics. And this is the regime where you go to stronger fields, where the continuum contribution becomes important, and this is where the so-called HAG process, the high harmonic generation process, which I showed in the first slide, starts to kick in. Okay. So this kind of gives you a demarcation as to when I can start getting this so-called high harmonic generation. When you deform the potential significantly, that you can have continuum contributions to your state, you can start seeing this new phenomena, which is not perturbative, which means your field is not weak. It's not small, creating a small distortion, but it's actually modifying the state significantly. And also the continuum contribution would imply that I am photoionizing. Okay? That is photoionization. So I am freeing up a part of the wave function to become a positive energy state, which would then just fly away from the parent atom.
But 0.008 is still we are talking about power in terms of 10 power 11, 10 power 11.
No, 0.1 would be already 10 to the 14.
So in case of like higher fields, even higher like 0.2 and stuff,
Yeah, then you just start blowing it up and you can't.
so it won't be like this.
Yeah, so you'll have more and more continuum contribution. Right? Yes. Okay, so that's like for the first little part from the simulation. So let's see what are the key takeaways from this. So if you have strong fields, that perturbative theory that we discussed in the last class will not be useful anymore, because you are seriously distorting the wave function. Okay, and that means you would need many terms in your series to be able to get an accurate description. Right? Continuum contributions become important, which means you are actually photoionizing the system. Right? Positive energy states means you are freeing up the electron, and that means you are ionizing the system. Now if you want to generate high harmonics, what do you need to do? You need to do this photoionization process in such a way that you have a certain nonlinear behavior built into your process. Right? In the last lecture we discussed that if I want second harmonic generation, I could have an excitation to two states through a certain in-between state, right? It absorbs two photons, right, omega and omega, and then gives back at 2 omega. So which means I need a second order process to be able to see a second harmonic. Same way, although I did not discuss, if I want a third harmonic generation, then I would need 3 levels and absorption of 3 photons, and then an emission of a joint energy of 3 omega to be able to generate a 3 omega photon, right? So which means if I want to get high harmonics, I need some nonlinear behavior built into it. So photoionization also need to do the same thing, except that this final state is not a bound state, but it's a continuum state. That means that I am photoionizing from a ground state to a continuum state through absorption of multiple photons. Right? I need to build in that nonlinear behavior so that I can get high harmonics. It's just that the bound state has been replaced by a continuum state. Okay. Now if I want to photoionize a typical atom, right, this is now coming to the numbers that the universe has provided, and if I have to ionize, then I need to pick some low frequency fields which fall in the near infrared regime, okay. And also because that is the kind of lasers that we have, that is how the kind of crystals that we have managed to master. So if I want a titanium sapphire laser, it is going to give you emission in the near infrared regime. So therefore, if we try to create a multi-photon ionization process instead of a multi-photon absorption process where the final state is a continuum state, right. So let me maybe draw one more picture. So this is a continuum state, this is the ground state, and it needs to absorb many photons to reach or to break this ionization threshold. So I have a multi-photon ionization process. So that is how I can build in that nonlinear behavior to be able to generate high harmonics. So the main idea is you need low frequency fields and strong fields, because the moment I have a higher order process, I need strong fields to be able to have that finite probability to be able to ionize a system. Now another important observation which I would like to take it as a fact, that if I look at any photoelectron spectrum, then the maximum probability of ionization happens when the momentum, photoelectron momentum, is 0. Okay. We will not be able to prove this in this lecture, but that is the general nature, that the maximum photoionization probability is for photoelectrons with near 0 photoelectron energy. That is just, you are just crossing that ionization threshold. Okay. Now in this lecture we will discuss high harmonic generation, and we will also show that some important features of this high harmonic generation, such as what is the cutoff associated with the high harmonic spectra and the chirp, can actually be described by a classical model. So we will discuss these two aspects, a little bit about the ionization aspect, a little bit about the classical model today. Okay, first the ionization. So when you have very low frequency fields, so let us take a hydrogen atom for example. This is a ground state, and that is a, let us say that is a 0 or near 0 photoelectron state. So what is the ionization potential for a hydrogen atom? That is about 13.6 eV, just giving you a few numbers. Now a typical titanium sapphire laser, which gives you radiation at 800 nanometers, corresponds to 1.5 eV, right, approximately. Now if I want to collect this much energy, 13.6 eV from 1.5 eV photons, then I would need almost 9 photons to be able to ionize it, right. So I have a multi-photon ionization process. Now it is also that because this wavelength is or the time period would correspond to about 2.5 femtoseconds, it is also a certain slow process. That means the electron can also see a field changing very slowly. So that means in the time frame of the electron, it sees the field kind of instantaneously, that I have a certain static field, right. It is a low frequency radiation. So therefore the electron is basically slowly, it is feeling the change in the electric field very slowly. So one can also make, it has two contributions, one is a multi-photon ionization process, and you can also have what is called a quasi-static tunneling process. So that means let us say you have one snapshot where the electron sees a particular field strength, right. So I have this oscillating field, that is electric field is oscillating, but let us say this frequency is very slow compared to what the time scales of an electron motion. So it is going to see, oh, at this point it is going to see this field, right, and it responds to that field, and it is very fast. So but the field is changing slowly. So therefore it kind of sees this instantaneous field, and at each field strength it sees such a tunnel barrier, and therefore it can tunnel through, this initial state can tunnel through, and you can have ionization through what is called tunnel ionization. So you have basically two competing processes, one is a multi-photon ionization and one is a quasi-static tunnel ionization process, and depending on the field strength and the frequency of the field, these two, one of them would be dominant versus the other. Now how do I know which one is dominant in a particular problem, right? There is a theory given by Keldysh, and he has defined a particular parameter called the Keldysh parameter, and this Keldysh parameter is given by this ratio of the ionization potential to twice the so-called ponder motive energy. Okay. So we'll discuss what ponder motive energy in the next slides. But this whole thing, this whole expression can actually be also converted into a ratio of the so-called tunnel time and the time associated with the frequency of the laser. Okay. T naught is the period associated with the laser field, and T tunnel is some characteristic time that is associated with tunneling. Okay. It's a ratio of these two which gives you this Keldysh parameter, and depending on this ratio, which is also equivalently square root of IP by 2 UP, one knows whether the tunnel ionization is the dominant process or whether the multiphoton ionization is the dominant process.